Picture a place in the universe where gravity is so overwhelmingly strong that nothing can escape its grasp, not planets, not stars, not even light itself. A place of absolute darkness, a cosmic abyss that seems to defy everything we know about existence. Now imagine that same darkness shining with a brilliance that outshines entire galaxies, blazing across the cosmos with the power of 1,000,000 suns. It sounds like something from science fiction, but this is real, one of the most astonishing and beautiful contradictions in all of nature. This is the mystery of quasars, and it challenges not only our understanding of black holes, but the very laws of physics as we know them. For centuries, human beings have looked up at the night sky and wondered about the nature of the universe. We've told stories about the stars, mapped the heavens, and built telescopes to bring distant worlds into view. Yet some discoveries are so profound, so utterly unexpected, that they force us to rethink everything. Quasars are one of those discoveries. They appear as tiny, star-like points of light, but in reality, they are the intensely bright hearts of distant galaxies, powered by supermassive black holes that are actively feeding on surrounding matter. How can something that traps light become the greatest source of light we've ever observed? That's the breathtaking paradox we're going to explore together. In this video, we'll journey to the edge of these gravitational monsters and peer into the processes that make them shine. We'll uncover how swirling disks of superheated gas convert matter into raw energy, how magnetic fields shape colossal jets that stretch across space, and how these cosmic engines challenge our most fundamental ideas about darkness and light. This isn't just a story about faraway objects, it's about the limits of human knowledge and our relentless curiosity to understand the universe. So join me as we dive into one of astronomy's most captivating puzzles and discover how, in the deepest darkness, light can be born. To understand how a black hole could possibly produce light, we first need to grasp what a black hole truly is. Picture the most powerful, inescapable gravitational pull you can conceive. A black hole is a region in space where that gravity has become so overwhelmingly strong that it warps the fabric of spacetime itself, creating a bottomless pit from which nothing can escape. The defining rule of a black hole is this absolute boundary, known as the event horizon. Think of it as the point of no return. Once any object, a spacecraft, a planet, or even a particle of light crosses this invisible threshold, it is pulled inexorably toward the central singularity, a point of infinite density where our known laws of physics simply break down. This is why black holes have earned their reputation as the ultimate cosmic vacuums, dark and invisible monsters lurking in the void. These incredible objects are born from death. When a truly massive star, many times larger than our Sun, reaches the end of its life, it doesn't fade away quietly. It goes out in a spectacular blaze of glory known as a supernova. In this cataclysmic explosion, the star's outer layers are blasted out into space, while its core, no longer supported by the outward pressure of nuclear fusion, collapses under its own immense weight. If the remaining core is massive enough, this collapse continues unchecked, crushing matter into an infinitesimally small point and giving birth to a stellar mass black hole. But the largest black holes, the supermassive ones that power quasars, have a more mysterious origin story. They are behemoths, weighing millions or even billions of times the mass of our Sun, and they are found at the very hearts of galaxies. Astronomers are still piecing together how they grew so large, so quickly in the early universe. For a long time, this classical view defined black holes in the scientific imagination. They were the ultimate endpoints of gravity, cosmic dead ends that simply swallowed everything that came too close. They were the darkest objects imaginable, not because they were black in color, but because they emitted no light whatsoever. They could only be detected indirectly by their gravitational influence on nearby stars and gas, or by the telltale X-rays emitted by material heated to incredible temperatures just before it vanished forever past the event horizon. This image of a black hole as a dark, destructive, and fundamentally simple void sets the stage for the incredible paradox we are about to unravel. Because if a black hole's gravity is so strong that it traps light, how can it be responsible for the most luminous phenomena in the entire cosmos? The answer lies not within the darkness of the hole itself, but in the frenzied, violent, and brilliantly lit chaos just outside its door. So what exactly are these brilliant enigmas we call quasars? The name itself offers our first clue. Quasar is actually a shortened version of the term quasi-stellar radio source. Back in the early 1960s, astronomers using radio telescopes began detecting incredibly powerful signals coming from what appeared to be faint, star-like points of light. They looked like ordinary stars in our own galaxy through an optical telescope, but their radio emissions were off the charts, unlike anything seen before. This strange combination, a star-like visual appearance paired with a massive radio output, earned them this quasi-stellar name, a label that stuck even after we discovered their true, far more extraordinary nature. The real breakthrough in understanding these objects came from an astronomer named Martin Schmidt at Caltech. In 1963, he was studying the spectrum of one of these radio-bright stars, known as 3C273. A spectrum breaks down an object's light, revealing telltale fingerprints of the chemical elements present. What Schmidt saw was baffling. The pattern was unmistakably that of hydrogen, the most common element in the universe, but it was shifted far toward the red end of the spectrum. This redshift meant the object was moving away from us at a tremendous speed, over 15% the speed of light, which in turn placed it at a truly staggering distance, billions of light years from Earth. The implication was earth-shattering. For an object that distant to appear that bright in our sky, it had to be emitting almost unimaginable amounts of energy, outshining entire galaxies containing hundreds of billions of stars. We now know that a quasar is not a star at all. It is the intensely luminous core of a distant galaxy, a region known as an active galactic nucleus. At the very center of this maelstrom of light lies a supermassive black hole, a gravitational titan with a mass millions or even billions of times that of our Sun. But the black hole itself isn't the source of the light, it's the engine. The prodigious energy output comes from the colossal disk of superheated gas and dust spiraling into the black hole's clutches, an accretion disk we touched on earlier. As matter is torn apart and accelerated to incredible speeds in this cosmic whirlpool, friction and immense gravitational forces heat it to temperatures of millions of degrees, causing it to glow with a ferocious brightness that can be seen across the universe. This discovery completely revolutionized the field of astronomy. Quasars became our most powerful beacons for illuminating the early history of the cosmos. Because their light has traveled for billions of years to reach us, they act as time machines, allowing us to peer back to an era when galaxies were young, and the universe was a much more violent and energetic place. Their existence proved that supermassive black holes weren't just theoretical curiosities. They were real, they were common, and they played a fundamental role in shaping the evolution of galaxies from the very beginning. The sheer fact that we can detect them from such immense distances speaks directly to the central paradox we're exploring: how the most effective trap for light in the universe can simultaneously power its most brilliant and enduring lights. But the sheer gravitational pull of a black hole is only half the story. The true source of a quasar's incredible light show isn't the darkness at the center, but the frenetic, chaotic, and dazzlingly bright arena that surrounds it, an immense structure known as an accretion disk. Picture a cosmic whirlpool of unimaginable scale, a vast, flattened disk of gas, dust, and the shredded remains of stars that have ventured too close. This material doesn't fall straight in. Instead, it's captured by the black hole's gravity and begins a long, spiraling descent, much like water circling a drain. As these particles are pulled inward, they rub against each other at tremendous speeds, creating immense friction. Combine this with the crushing gravitational forces, and the temperature of this swirling maelstrom soars to millions of degrees. At these extreme temperatures, the disk doesn't just get hot. It becomes a furnace that incandesces across the entire electromagnetic spectrum. It glows with a ferocious white-hot light, emitting everything from radio waves and infrared to visible light, ultraviolet, and powerful X-rays. This is the fundamental mechanism that solves the first part of our paradox. The light we see from a quasar isn't coming from inside the black hole. It's being generated outside the event horizon by this incredibly energetic process. The accretion disk is essentially a giant power plant, and its fuel is gravity itself. As matter loses gravitational potential energy during its inward spiral, that energy isn't destroyed, it's converted, following Einstein's famous equation, into an enormous amount of radiation. In fact, this process is astoundingly efficient. While nuclear fusion, the process that powers stars, converts only about 0.7% of mass into energy, the conversion within an accretion disk can be up to 40% efficient. This is why a relatively small amount of matter can produce such a staggering outpouring of light, outshining entire galaxies. The structure of the disk itself is a fascinating study in extremes. The material closest to the event horizon orbits at a significant fraction of the speed of light, whipped around by the black hole's incredible spin, while the outer regions move more slowly. This difference in velocity creates shear forces that further heat the gas and contribute to the turbulence. The inner edge of the disk is the hottest and brightest, blazing with X-rays, while the outer, cooler regions emit longer wavelengths of light. It's a dynamic, seething environment where physics is pushed to its absolute limit, and it serves as the primary engine that transforms the black hole's destructive appetite into the most brilliant beacons in the cosmos. But the brilliance of the accretion disk is only part of the spectacle. To truly grasp the full power of a quasar, we must look above and below this swirling disk of light to witness one of the most dramatic and violent events in the universe, the eruption of relativistic jets. Imagine two colossal searchlight beams of pure energy erupting from the poles of the black hole system and shooting out into the void at nearly the speed of light. These are not gentle streams, they are tightly focused, unimaginably powerful cannons firing a torrent of ionized matter and radiation across tens of thousands of light years, often far beyond the boundaries of their host galaxy. These jets are born from the chaos of the accretion disk itself, but they are shaped and launched by the incredible magnetic fields generated by the system's frantic rotation. As the superheated plasma in the disk spins at relativistic speeds, it twists the magnetic field lines into a tightly wound, incredibly powerful structure, like a cosmic spring coiling with immense tension. Near the black hole's poles, where this magnetic pressure can find a path of least resistance, this energy is released in a spectacular outburst. The magnetic fields act as a slingshot, funneling material and accelerating it along these narrow channels, propelling it outward with a force that defies the black hole's own gravitational pull. The particles within these jets, electrons and protons stripped from their atoms, are accelerated to velocities so close to the speed of light that the rules of Einstein's special relativity come into dramatic play. From our perspective, time for these particles slows down dramatically and their energy skyrockets. As these ultra-high energy particles are forced to spiral along the powerful magnetic field lines within the jet itself, they release a unique and brilliant form of light known as synchrotron radiation. This is the same type of radiation produced in particle accelerators on Earth, but on a cosmic scale. This process floods space with light across the entire spectrum, from long radio waves to high-energy gamma rays, making these jets incredibly bright and detectable across mind-boggling distances. The sheer scale of these structures is what truly cements their status as one of the universe's most energetic phenomena. A single jet can stretch for hundreds of thousands, even millions of light years, punching through intergalactic space and often slamming into tenuous clouds of gas, creating immense, glowing lobes of radio emission that act as cosmic signposts. In some cases, these jets are so powerful that they can influence the evolution of entire galaxy clusters, heating the surrounding gas and preventing it from cooling to form new stars. When we observe a quasar, a significant portion of the brilliant light we see, particularly in the radio and X-ray portions of the spectrum, is coming directly from these magnificent and violent outflows. They are the ultimate testament to the fact that a black hole is not just a passive consumer of matter, but an active, dynamic engine that can reshape its entire cosmic neighborhood with breathtaking force. So far, we've seen how the superheated accretion disk provides the raw power and how relativistic jets act as cosmic particle accelerators. But none of this would be possible without the invisible architect of this entire chaotic system, the magnetic field. Think of it as the conductor of this immense cosmic orchestra, directing the flow of matter and energy with an unseen hand. These fields are generated by the motion of the incredibly hot, ionized gas within the accretion disk itself. As this charged plasma churns and spins at near light speed, it behaves like a dynamo, generating magnetic fields that become twisted, amplified, and woven into the very fabric of the black hole's environment. One of the most critical jobs these magnetic fields perform is acting as a cosmic conveyor belt for the jets. The intense rotation of the disk and the black hole's own spin wind these magnetic field lines up like an enormous, tension-filled spring. This coiled energy needs a release valve, and it finds one at the black hole's poles. Here, the magnetic fields act as a focus channel, a rigid structure that can defy the pull of gravity. They grab hold of charged particles from the inner edge of the accretion disk and slingshot them outward, accelerating them to relativistic speeds and collimating them into those incredibly narrow, powerful beams we observe shooting across space. Without these magnetic fields to guide and focus the outflow, the energetic material would likely just spray out in all directions, a disorganized cloud rather than a light-speed lance capable of piercing intergalactic space. But the influence of magnetism goes even deeper, right into the heart of the accretion process itself. This is where a fascinating phenomenon called the magnetorotational instability comes into play. In a simple, non-magnetic disk, gas closer to the black hole would orbit much faster than gas farther out. This difference in velocity would naturally cause the disk to shear, but it wouldn't necessarily be enough to create the intense turbulence and friction required to explain the incredible heating we see. The magnetorotational instability, or MRI for short, solves this. The weak magnetic field permeating the gas creates a kind of cosmic glue between different layers of the disk. When one section of gas tries to slide past another, these magnetic field lines get stretched, creating a tension that transfers energy and angular momentum outward. This process acts as a powerful engine for turbulence, vigorously stirring the disk and dramatically increasing the internal friction. This heightened friction is what supercharges the heating process, turning the disk into a far more efficient engine and directly contributing to the quasar's phenomenal luminosity. And just when you think the system couldn't get any more energetic, magnetic fields have one more spectacular trick to play: magnetic reconnection. Picture two powerful magnetic field lines running in opposite directions. They can be forced together by the chaotic motion of the plasma, and when they meet, they can suddenly snap and reconfigure into a new, lower energy arrangement. This sudden release is like cutting a tensed rubber band. A massive amount of stored magnetic energy is unleashed in a violent burst, accelerating nearby particles to incredible speeds. These reconnection events are essentially colossal short circuits happening in the corona above the accretion disk, and they are thought to be responsible for some of the most intense and rapid flares of X-ray and gamma-ray radiation we detect from these active systems. They add another layer of brilliant, unpredictable complexity to the already overwhelming light show, proving that the magnetic environment around a black hole is as dynamic and powerful as the gravity that defines it. Now that we've seen how magnetic fields orchestrate the brilliant chaos around a black hole, it's time to address a fundamental question. Why is it that some black holes become these incredible cosmic lighthouses, while others remain dark and seemingly dormant? The answer lies in a critical distinction between two vastly different classes of these gravitational giants: the supermassive black holes that power quasars and the much smaller stellar mass black holes that dot our galaxy. Understanding this difference is like comparing a campfire to a volcanic eruption. While both involve combustion, the scale, fuel source, and resulting spectacle are worlds apart. Let's start with the smaller, more common variety, stellar mass black holes. These are the remnants of massive stars that have lived out their lives and died in spectacular supernova explosions. When a star at least 20 times more massive than our Sun exhausts its nuclear fuel, the outward pressure from fusion can no longer counter the immense inward pull of its own gravity. The core collapses catastrophically in on itself. If the remaining mass is sufficient, it crushes down into a singularity, birthing a black hole typically between about 5 and 100 times the mass of our Sun. These objects are scattered throughout galaxies, often isolated or locked in a binary dance with a companion star. Their gravitational influence is powerful but localized. They can pull streams of gas from a nearby star, creating a small, hot accretion disk that glows faintly in X-rays, what astronomers call an X-ray binary. While certainly dramatic, this is a modest affair compared to the universe-shaking brilliance of a quasar. A stellar black hole is like a solitary predator, occasionally snacking on whatever wanders too close, but largely existing in the dark, its presence known only by its subtle effects on its immediate surroundings. In the opposite corner of the ring, we have the true titans, supermassive black holes. These are not the products of a single star's death, but are fundamental building blocks of galaxies themselves, residing at the very heart of nearly every large galaxy, including our own Milky Way. Their origins are a topic of active research, potentially forming from the collapse of immense primordial gas clouds in the early universe, or from the rapid growth of smaller seed black holes through countless mergers and accretion episodes. Their defining characteristic is their sheer, almost incomprehensible mass. Where a stellar black hole might be 10 solar masses, a supermassive black hole weighs in at millions to billions of solar masses. Our own Sagittarius, a star, for instance, is a relatively quiet 4 million solar mass giant at the center of our galaxy. To put that scale into perspective, if a stellar black hole is the size of a large city, A supermassive black hole would be the size of our entire solar system. This immense mass is the first prerequisite for creating a quasar, but mass alone isn't enough. The second, and perhaps more crucial, ingredient is a colossal and steady supply of fuel. A supermassive black hole sitting at the dynamic center of a galaxy is in a prime position for a feast. It is surrounded by a dense, bustling environment, swarms of stars, vast clouds of gas, and entire nebulae all whirling around the galactic core. Galactic collisions and mergers can funnel unimaginable quantities of this material directly toward the central black hole. It is this abundant, ongoing influx of matter that allows a supermassive black hole to build a massive, stable, and incredibly energetic accretion disk. The scale of this disk is what separates a flicker from a blaze. With so much fuel continuously pouring in, the disk can grow to be enormous, generating friction and heat on a proportionally gigantic scale, ultimately converting matter into radiation with breathtaking efficiency. A stellar black hole, by contrast, is often fuel-starved. It might briefly flare up if it rips apart a passing star, but these events are temporary. It simply cannot access the sustained buffet of material required to power a persistent, galaxy-dominating engine. This distinction in mass and fuel availability leads directly to the final, most visible difference: energy output. The luminosity of an accreting black hole is directly tied to the rate at which it is consuming matter. A stellar black hole in a binary system might outshine our Sun in X-rays during an outburst, but it will never compete with the combined light of every star in its host galaxy. A supermassive black hole in its active quasar phase, however, can do exactly that. It can unleash so much energy that its brilliance drowns out the light of hundreds of billions of stars, making it visible from the farthest reaches of the observable universe. It is this perfect storm, a monster-sized gravitational anchor positioned in the wealthiest neighborhood of a galaxy and receiving a continuous delivery of cosmic fuel, that allows a black hole to transcend its dark nature and become the most luminous object in existence. This is why the supermassive variety can light up the cosmos, while their stellar mass cousins, for all their power, typically remain hidden in the shadows. Even the most powerful cosmic engines are governed by fundamental laws of physics, and for a quasar to sustain its incredible brilliance without self-destructing, it must navigate a delicate balancing act defined by the Eddington Limit. Named after the renowned astrophysicist Sir Arthur Eddington, this principle describes the maximum possible luminosity an astronomical object can achieve when it reaches a state of perfect equilibrium. Imagine a star, or in our case, a blazing accretion disk around a black hole. As it shines, it doesn't just emit light. That radiation exerts a subtle but constant outward pressure on the very material that's feeding it. Gravity, of course, is pulling that material inward. The Eddington Limit is the precise point where these two opposing forces, the outward push of radiation and the inward pull of gravity, cancel each other out. At this limit, the system achieves a kind of stable balance. Any brighter, and the radiation pressure would theoretically be strong enough to overcome gravity and push the inflowing gas and dust away, effectively shutting off the fuel supply and causing the brilliant light to fade. This concept is crucial for understanding the stability of quasars. For a given black hole mass, there is a calculable maximum luminosity it can sustain through spherical accretion before it begins to blow its own fuel source apart. This limit scales directly with the mass of the central object. A more massive black hole has a stronger gravitational grip, so it can hold onto its accretion disk against a much more intense outward radiation pressure, allowing it to have a far higher maximum luminosity. This is precisely why supermassive black holes are the only ones capable of powering quasars. Their immense mass grants them an enormously high Eddington limit, permitting the sustained, galaxy-dominating brightness we observe. It acts as a built-in cosmic regulator, ensuring that these engines don't simply burn out in a brief, suicidal flash of glory, but can shine steadily for millions of years, lighting up the early universe. Yet, the universe is rarely so simple and orderly. While the Eddington Limit defines a theoretical ceiling for stable accretion, black holes, particularly in their youth, are known to be messy and violent eaters. During periods known as hyperaccretion, often triggered by a sudden and massive influx of fuel like a galactic collision or the tidal disruption of an entire star, a black hole can consume matter at a rate that pushes it beyond this limit. In these extreme episodes, the accretion disk becomes so incredibly luminous that the radiation pressure does indeed begin to overpower gravity in the outer regions. This doesn't immediately stop the process. Instead, it creates a profoundly unstable and dynamic environment. The intense radiation drives powerful outflows and winds, ejecting a significant fraction of the incoming material back into space in a frantic, energetic feedback loop. It's a cosmic feast where the table is being shaken violently, and much of the food is sent flying off before it can be consumed. These temporary excursions beyond the Eddington Limit are thought to be responsible for some of the most intense and variable outbursts we see in quasars. The system doesn't calmly hover at the limit, it oscillates around it with periods of intense feeding and brightening followed by moments where radiation wins and shuts down the inflow, causing a dimming. This cyclical behavior adds another layer of complexity to the brilliant paradox, showing that the light output is not always smooth and stable, but can be subject to violent fits and starts. The ability to occasionally exceed this limit is a testament to the raw, unbridled power at work, demonstrating that while physics sets the rules, black holes often find a way to bend them, creating some of the most spectacular and energetic events in the cosmos without completely tearing themselves to pieces. But how do we, from our tiny vantage point on Earth, gather the concrete evidence that allows us to make such grand claims about these distant monsters? The answer lies in the sophisticated toolkit of modern astronomy, a collection of methods that transform faint whispers of light into a detailed story of cosmic power. The journey to understanding a quasar begins with its most basic property, its light. When that light is captured by our telescopes, it holds within it a wealth of hidden information, and the master key to unlocking it is a technique called spectroscopy. Imagine taking the pure white light from a quasar and passing it through a prism, splitting it into a full rainbow spectrum. To the naked eye, it might just look like a continuous band of color, but to an astronomer, this spectrum is a detailed barcode, a unique fingerprint etched with dark and bright lines that tell an epic story. These lines are created by specific chemical elements in and around the quasar, each one absorbing or emitting light at a precise wavelength. By identifying these lines, finding the signature of hydrogen, helium, carbon, and iron, we can determine the composition of the superheated gas in the accretion disk and the surrounding cloud. But the most crucial piece of information comes from noticing that this entire pattern of lines is not where it's supposed to be. It is shifted, often dramatically, toward the red end of the spectrum. This redshift is our primary indicator of distance. It occurs because the universe itself is expanding, stretching the wavelengths of light as it travels for billions of years to reach us. The greater the redshift, the farther away the quasar and the further back in time we are looking. It was this very measurement that first revealed the true nature of quasars to Martin Schmidt, proving they were not nearby stars but the most distant and energetic objects ever identified. Spectroscopy doesn't stop there. The width and shape of these spectral lines also tell us about the incredible velocities of the gas swirling near the event horizon, providing indirect evidence of the supermassive black hole's powerful gravity. However, the visible light we see is only a tiny fraction of the story. A quasar's energy floods across the entire electromagnetic spectrum, from long, low-energy radio waves to incredibly short, high-energy gamma rays. To get a complete picture, we must become cosmic multi-wavelength detectives, using a fleet of specialized telescopes, each designed to see a different slice of this energetic pie. For the searing X-rays produced in the million-degree corona just above the accretion disk, we rely on space-based observatories like the Chandra X-ray Observatory. Chandra's sharp eyes can pinpoint the precise location of this high-energy emission, allowing us to map the innermost regions of the quasar engine and even measure the spin of the central black hole. To study the colossal relativistic jets that can stretch for millions of light years, we turn to radio telescopes. Networks of dishes like the Very Large Array in New Mexico can combine their signals to achieve incredible resolution, creating detailed images that show the intricate structure of these jets, from their launch point near the black hole to the massive lobes where they finally collide with intergalactic space. On the other end of the spectrum, the Fermi Gamma Ray Space Telescope monitors the sky for the most violent and explosive outbursts, capturing the extreme photons generated by particles within the jets being accelerated to virtually the speed of light. And of course, for the stunning visible and ultraviolet light that makes quasars shine so brightly, the Hubble Space Telescope has been an indispensable workhorse. Hubble's crystal-clear vision, unobscured by Earth's atmosphere, has not only pinpointed the host galaxies surrounding quasars, proving they reside at the hearts of galaxies, but has also used the phenomenon of gravitational lensing to its advantage. In several famous cases, the gravity of a foreground galaxy has bent and magnified the light of a more distant quasar, creating multiple images or dramatic arcs of light. This natural telescope allows us to peer into the quasar's structure in far greater detail than would otherwise be possible, providing a zoomed-in view of the engine room itself. It is this symphony of data, gathered from telescopes orbiting Earth and dotting its surface, that provides the irrefutable evidence for the black hole paradox. By combining the distance from spectroscopy with the luminosity measurements across all wavelengths, we can calculate the staggering energy output. By analyzing the X-rays, we probe the intense gravity near the event horizon. By mapping the radio jets, we understand the directed outflow of energy. Each observation is a different piece of the puzzle, and when fit together, they form a consistent and awe-inspiring picture. A dark gravitational pit surrounded by a whirlpool of light, capable of outshining the combined might of every star in its galaxy. These are not theoretical constructs, they are physical realities, their secrets teased out by our technology and ingenuity, confirming that in the darkest corners of the universe, light finds a way to triumph. Their incredible luminosity and mind-boggling distance make quasars far more than just fascinating objects of study. They are indispensable tools for cosmologists, acting as the universe's ultimate lighthouses. Shining across billions of light years, their brilliant beams cut through the cosmic dark, illuminating not just themselves but everything their light touches on its long journey to our telescopes. This unique utility transforms them from passive subjects into active probes, allowing astronomers to conduct experiments on the largest scales imaginable and piece together the history and structure of the cosmos itself. Think of it like this: if you were a scientist trying to understand the properties of a vast, mostly empty room, you might shine a powerful spotlight from one side to the other. By carefully analyzing the light that reaches you, noting if it's been dimmed, colored, or otherwise altered by passing through pockets of dust or haze in the room, you could learn a great deal about the room's contents without ever having to walk through it. Quasars provide that spotlight for the universe, Their light serves as a perfect background source, traveling for eons through the near-perfect vacuum of intergalactic space, a region known as the intergalactic medium. This isn't a complete void. It's strewn with incredibly diffuse clouds of primordial gas, mostly hydrogen and helium left over from the Big Bang. As the quasar's light journeys toward us, it passes through these tenuous clouds. Specific elements within the clouds absorb very particular wavelengths of that light, imprinting a unique chemical signature onto the beam. When we finally capture this light with our spectrographs, we don't just see the quasar's own spectrum. We see a series of dark absorption lines superimposed upon it like a barcode. Each set of lines tells us exactly what element created it, and thanks to redshift, exactly how far away that cloud of gas is located. This allows astronomers to create a detailed three-dimensional map of this otherwise invisible cosmic web, tracing the distribution of matter across the vast, empty stretches between galaxies. It's a powerful technique that reveals the large-scale skeleton of the universe, a filamentary structure that galaxies themselves are strung along like pearls on a string. This method is particularly crucial for studying the most elusive phase of cosmic history, the epoch of reionization. In the very early universe, space was filled with a hot, dense fog of neutral hydrogen gas that made it opaque to light. Something had to clear that fog, and the leading suspects are the first generations of stars and galaxies, and potentially the very first quasars. Their intense ultraviolet radiation is thought to have played a key role in reionizing the universe, stripping electrons from those neutral hydrogen atoms and turning the intergalactic medium into the transparent state we see today. By studying the absorption lines in the light of the most distant quasars, those whose light was emitted during this cosmic dawn, astronomers can directly observe the final patches of this primordial fog as they were being evaporated away. They can see the precise point in time when the lights truly came on across the cosmos, a fundamental transition that made the universe as we know it even possible. Beyond mapping the cosmic web and probing reionization, quasar light also acts as a cosmic time capsule, preserving a record of the universe's chemical evolution. The absorption lines we detect aren't just from hydrogen and helium. We also find traces of heavier elements like carbon, oxygen, and silicon. This is astonishing because these elements were not forged in the Big Bang. They were created later in the nuclear furnaces of stars and scattered across space by supernova explosions. Finding them in the intergalactic medium billions of years ago tells us that even at very early times, the universe had already been seeded with the building blocks of planets and life by generations of massive stars that lived and died quickly. Quasars, by holding this ancient light up for us to read, provide a direct record of how the universe became enriched with the very elements we are made of. This role as a universal probe underscores the beautiful duality of quasars. They are not merely paradoxical engines of destruction and creation, they are also beacons of knowledge. Their extreme nature serves a profound purpose, granting us a window into the most inaccessible eras of cosmic history and allowing us to trace the architecture of reality on its grandest scale. They illuminate the dark, connect the distant, and reveal the story of everything, proving that sometimes to understand the universe's deepest secrets, you must follow the brightest lights. But just when we think we have a complete picture, a brilliant theoretical insight from Stephen Hawking reminds us that our understanding is always evolving, and that even the most established ideas can be turned on their head. For decades, the classical view of general relativity held absolute sway. A black hole is a black body, a perfect trap from which nothing, not even a single photon, could ever return. Its event horizon was the ultimate one-way street, and the notion that a black hole could emit anything seemed like a contradiction in terms. Hawking's genius was to ask what happens when you introduce the bizarre rules of quantum mechanics into this seemingly settled picture, and the answer he found was as shocking as it was elegant. Black holes can, in fact, glow. Hawking radiation, as it's now known, arises from the strange and probabilistic nature of reality at the smallest scales. According to quantum theory, empty space is not truly empty. Instead, it is a seething, bubbling foam of virtual particles, pairs of particles and antiparticles that spontaneously pop into existence, borrowing energy from the vacuum, only to annihilate each other and disappear again in an incredibly short span of time. This is happening everywhere, all the time, and normally these particles have no lasting effect. But Hawking realized that something extraordinary occurs when this quantum fluctuation happens right at the precipice of a black hole's event horizon. In these fleeting moments, one of the virtual particles might be created just outside the horizon, while its partner is created just inside. The particle outside, if it has enough energy, can escape the black hole's gravitational pull and fly off into space, effectively becoming real. Its unfortunate partner, however, falls past the point of no return, carrying negative energy with it. To conserve energy, the black hole must pay for the escaped particle's mass and energy. It does so by losing a tiny, tiny amount of its own mass. From the perspective of a distant observer, it appears as if the black hole has just emitted a particle of radiation. This process is incredibly slow and faint for a large black hole, a barely perceptible whisper of heat. The temperature of this Hawking radiation is inversely related to the black hole's mass. For a stellar mass or supermassive black hole, this temperature is far colder than the cosmic microwave background radiation that fills the universe, meaning they absorb more energy from space than they emit, and their net evaporation is negligible over timescales longer than the current age of the universe. It is only for hypothetical, tiny primordial black holes that this process would be dramatic and rapid, leading to a final, explosive flash of energy. This revelation created a profound tension, now known as the black hole information paradox. If a black hole steadily evaporates away through Hawking radiation until it completely disappears, what happens to all the information about the material that fell into it? The rules of quantum mechanics state that information cannot be destroyed. It must be preserved in some form. But according to Hawking's early calculations, the radiation being emitted was purely thermal, a featureless glow that contained no information about what made up the black hole. It was as if you burned a priceless, intricate novel, and all that was left was the generic heat from the fire. This suggested a fundamental conflict between the smooth, deterministic geometry of general relativity and the information-preserving principles of quantum mechanics, a conflict that points toward the need for a deeper, unified theory of quantum gravity. So, we are left with a beautiful and layered paradox. The brilliant, classical light of a quasar, which we can see from billions of light-years away, is generated outside the event horizon by the immense forces of gravity and magnetism in the accretion disk and jets. Meanwhile, the faint, quantum glow of Hawking radiation is theoretically generated at the event horizon itself, a subtle process that for all large black holes is utterly drowned out by the surrounding cosmic fireworks. One is a testament to the raw power of gravity, the other a whisper from the quantum void. One defies our classical intuition by creating light from darkness. The other defies our quantum intuition by suggesting that information might be lost. Together, they paint a picture of black holes not as simple, destructive endpoints, but as the most complex and mysterious objects in the universe, where our two most successful theories of physics meet and struggle to find a common language. forever challenging and expanding our understanding of reality itself. The journey to understanding quasars is a perfect example of how science often advances, through a series of bewildering puzzles, brilliant deductions, and the gradual, painstaking work of connecting the dots. It all began in the late 1950s and early 60s with the dawn of radio astronomy. For the first time, we could listen to the universe, not just look at it, and astronomers were eagerly cataloging the sources of these mysterious radio signals coming from the depths of space. Many were linked to familiar objects, like the remnants of supernova explosions within our own galaxy, but a number of these powerful radio emitters were perplexing. When pointed toward them with optical telescopes, they didn't show a sprawling nebula or a distant galaxy. They appeared as nothing more than faint, unassuming, star-like points of light. They were christened quasi-stellar radio sources, a name that perfectly captured their confusing hybrid nature. They looked like stars, but their radio emission was unlike any star we knew. They were cosmic enigmas, and their true identity was a secret waiting to be unlocked. The key that finally cracked the code was held within their light, but it was a code that seemed impossible to decipher. Astronomers took spectra of these objects, breaking their light down into its constituent colors to reveal the chemical fingerprints of the elements present. The results were deeply strange. The patterns of emission lines were completely unrecognizable. They didn't match the signature of any known element. For years, these spectra were a source of immense frustration. Some researchers even humorously suggested they might be seeing the signatures of unknown elements from advanced extraterrestrial civilizations, a testament to just how baffling the problem was. The true meaning was hiding in plain sight, but it required a radical shift in perspective to see it. That shift came from the brilliant work of Dutch astronomer Maarten Schmidt at the California Institute of Technology in 1963. He was studying one of the most famous of these objects, known as 3C273, which had a particularly intense and puzzling spectrum. Staring at the pattern of lines, he had a sudden, revolutionary realization. The lines weren't from some exotic new element. They were the extremely familiar lines of hydrogen, the most common element in the universe. But they weren't where they were supposed to be. The entire pattern had been shifted dramatically toward the red end of the spectrum. This was a redshift, and it was enormous. Using the same principle that tells us a siren's pitch drops as an ambulance moves away from us, the redshift told Schmidt that 3C273 wasn't a nearby star at all. It was rushing away from us at over 15% the speed of light and was located an astounding 2 billion light-years away. This single calculation changed everything. For an object at that distance to appear as bright as it did in our telescopes, it had to be emitting a simply staggering amount of energy, far more than any ordinary galaxy. The only conceivable engine powerful enough to explain such luminosity was the gravitational energy released by matter falling into a supermassive black hole. Schmidt's breakthrough didn't just solve the mystery of one object. It flung open the doors to a new understanding of the universe. It revealed that the cosmos was far more violent and energetic in its youth than anyone had imagined, populated by these incredible galaxy core engines. Other astronomers quickly found similarly immense redshifts in other quasi-stellar sources, confirming they were all incredibly distant and luminous. The term quasar was born, and the field of active galactic nuclei was established, forever changing our view of black holes from theoretical oddities to central players in galactic evolution. This historical arc from confusion to clarity mirrors the very paradox we're exploring. It shows how an object that appeared as a mere pinpoint of light, a mystery that defied classification, could, upon deeper investigation, reveal itself to be one of the most powerful and fundamental forces shaping the entire cosmos. Yet, even as we unravel the intricate mechanics of the black hole itself, we must widen our view to an even grander cosmic stage, for these brilliant engines do not exist in isolation. They are embedded within the largest structures in the universe, whose form and fate are dictated by its most mysterious components, dark matter and dark energy. While they don't directly power the light-emitting paradox, they set the entire cosmic table upon which the feast of accretion occurs, influencing when, where, and how brightly a supermassive black hole can shine. Let's begin with dark matter, the invisible, mysterious substance that makes up about 85% of all the matter in the cosmos. We cannot see it directly because it does not emit, absorb, or reflect light, hence its name. But we know it's there because of its profound gravitational influence on the things we can see. It's the cosmic scaffolding upon which galaxies are built. Every galaxy, including our Milky Way, is nestled within an enormous, diffuse sphere of this dark matter called a halo. This halo is far larger than the visible galaxy itself, and its immense gravitational pull is what holds the galaxy together, preventing stars from flying off into the void as it spins. This dark matter halo plays a crucial, behind-the-scenes role in feeding the monster at the galaxy's center. The halo's gravity acts as a vast cosmic reservoir, funneling ordinary gas and dust, the baryonic matter that can form stars and accretion disks, toward the galactic center over billions of years. Think of it as a gigantic, invisible funnel. The size and mass of a galaxy's dark matter halo directly influence how much fuel is available in the central regions. A more massive halo will pull in more gas, creating a denser, richer environment around the supermassive black hole. This provides the sustained fuel supply necessary to power a bright, long-lived quasar phase. Furthermore, when galaxies merge, a common occurrence in the early, crowded universe, their dark matter halos also merge. This colossal event violently shakes up the gas within both galaxies, driving tremendous amounts of material directly toward the central black holes, potentially triggering a spectacular outburst of quasar activity. In this way, dark matter, though invisible and detached from the brilliant mechanics of the accretion disk, is the ultimate puppet master. It governs the growth of galaxies and, by extension, dictates the feeding schedule of the supermassive black holes at their hearts, setting the stage for the paradox to unfold. On an even larger scale, we encounter the most mysterious force in the universe, dark energy. This is not matter at all, but a repulsive force that seems to be inherent to the fabric of space itself. Its discovery in the late 1990s was another monumental shock to astronomy. By observing distant supernovae, astronomers found that the expansion of the universe is not slowing down due to gravity, as everyone had expected, but is actually accelerating. Something was pushing galaxies apart from one another at an ever-increasing rate. That something is what we call dark energy. This accelerating expansion has a direct and profound impact on our observation of quasars and the very paradox we are studying. Because dark energy is causing the universe to stretch apart faster and faster, it fundamentally alters the relationship between distance and time for the most distant objects. The light from a quasar 10 billion light-years away has been traveling for 10 billion years to reach us, showing us the universe as it was in its youth. But due to the accelerating expansion, that quasar is now actually much, much farther away than 10 billion light-years. This affects how we calculate its true luminosity and distance. Dark energy also shapes the future of the cosmos and the fate of these brilliant objects. As the expansion accelerates, galaxies will be pulled ever farther apart. In the far, far future, galactic collisions, those prime triggers for quasar activity, will cease entirely as galaxies become isolated islands in a vast, ever-growing void. The age of quasars, of brilliant active galactic nuclei, will eventually come to an end, not because the black holes disappear, but because dark energy will have cut off their fuel supply by isolating them from their cosmic neighbors. So, while the dazzling light of a quasar is born from the immediate, violent physics around a black hole, the broader narrative of its existence is written by the invisible hand of dark matter and the relentless push of dark energy. One provides the gravitational infrastructure for growth, while the other dictates the expanding cosmic arena in which that growth occurs. They are the unseen directors of the cosmic play, setting the conditions that allow a black hole's darkness to generate such brilliant light, and ultimately determining the long-term fate of these most luminous and paradoxical objects in the universe. But to truly grasp the complex ballet of forces swirling around a black hole, the superheated plasma, the twisted spacetime, the unimaginably powerful magnetic fields, we cannot rely on observation alone. The environment is too extreme, the scales too vast, and the events too violent to ever replicate in a laboratory. This is where the power of the modern computer becomes our greatest ally, allowing us to build virtual universes where we can test our theories against the harsh laws of physics. Through sophisticated simulations, we can peer into the heart of the accretion disk and witness the birth of relativistic jets in ways our telescopes can only dream of. One of the most powerful tools in this virtual toolbox is something called General Relativistic Magnetohydrodynamics, or GRMHD for short. The name is a mouthful, but it perfectly describes what it does. It's a computational framework that marries three incredibly complex fields of physics. First, it incorporates Einstein's theory of general relativity, which is essential for accurately modeling the warping of space and time around a massive black hole. Without this, our simulation would have no realistic gravity. Next, it brings in magnetohydrodynamics, which is the study of how electrically conducting fluids, like the superheated plasma in an accretion disk, behave in the presence of magnetic fields. Finally, it combines these into a single, cohesive model that can run on some of the world's most powerful supercomputers. These simulations are not simple cartoons. They are intricate mathematical representations of reality. Researchers define the initial conditions, the mass and spin of the black hole, the amount and properties of the surrounding gas, the strength of the initial magnetic fields. Then they set the rules, the equations of general relativity and magnetohydrodynamics, and let the simulation run. Over millions of computational hours, the virtual system evolves. We can watch as turbulence within the disk, driven by the magnetorotational instability, causes gas to heat up and begin its inward spiral. We can see how the black hole's spin drags the very fabric of spacetime around with it, an effect known as frame dragging, which can tilt and warp the inner disk. Most spectacularly, these models show us how the magnetic fields, wound up tighter and tighter by the disk's rotation, eventually snap and launch powerful jets of matter from the poles, exactly as we observe in real quasars. The value of these digital laboratories is immense. They allow us to conduct experiments that are impossible in the real world. What happens if we double the black hole's spin? How does the jet formation change if the magnetic field is stronger or weaker? What occurs during a tidal disruption event when a star is ripped apart and swallowed? By tweaking the variables, we can see the outcomes and compare them to actual observational data from telescopes like Chandra or the Event Horizon Telescope. When the simulation produces a jet structure or a spectrum of light that matches what we see in a real quasar, It gives us tremendous confidence that our underlying theories about gravity, magnetism, and plasma physics are on the right track. They are the essential bridge between raw mathematical theory and the glorious, chaotic reality we observe in the night sky, providing the crucial insights needed to finally decipher the mechanics behind the universe's most brilliant paradox. If you were to watch a quasar over time, you wouldn't see a steady, unchanging beacon. Instead, you'd witness a dynamic and often unpredictable cosmic light show, with its brilliance waxing and waning over periods that can range from just a few days to many years. This flickering is not a sign of weakness. It's a direct window into the violent and chaotic processes happening at the very edge of the event horizon. The brightness of a quasar is a direct reflection of its feeding rate. Think of it like a campfire. If you gently add one log at a time, the fire burns steadily. But if you suddenly dump a whole pile of wood onto it, it will roar to life in a brilliant, crackling burst before settling down again. A quasar operates on the same principle, but with the fury of a universe-scale inferno. This variability can happen for several dramatic reasons. Sometimes the change is driven by a sudden and massive influx of fuel. A star that wandered too close to the supermassive black hole can be torn apart by immense tidal forces in a cataclysmic event known as a tidal disruption event. This single act delivers a gigantic meal to the black hole all at once, causing the accretion disk to flare with incredible brightness as it desperately tries to process this unexpected bounty, a surge of light that can then slowly fade over months or years as the stellar debris is consumed. At other times, the instability is baked into the disk itself. The magnetorotational instability that drives turbulence can also create clumps and density waves within the swirling plasma. As these chaotic structures move through the disk, they can temporarily block our view of the brighter inner regions or themselves become intensely heated, causing random and rapid flickers in the overall light output. Perhaps the most dramatic changes occur when the jets themselves are involved. The process that launches and sustains these relativistic beams is incredibly complex and can be prone to its own instabilities. Changes in the magnetic field structure near the base of the jet or a sudden reconnection event can cause a massive injection of energy, making the entire jet brighten suddenly. We can sometimes even watch as bright knots of material form within the jet and travel outward at near light speed, their passage marked by a temporary spike in brightness. All of this variability is more than just a fascinating spectacle. It is a powerful diagnostic tool for astronomers. The speed at which an object can change its brightness tells us something fundamental about its size. This is based on a simple but powerful principle in physics. An object cannot change its overall brightness faster than the time it takes for light to travel across it. Imagine a light bulb the size of our solar system. If it were to suddenly turn off, the side closest to us would go dark immediately, but the light from the far side would take hours more to reach us, meaning the bulb would appear to fade gradually. Now imagine a tiny light bulb only a few miles across. It could flicker on and off in a fraction of a second. When astronomers see a quasar double its brightness in a matter of days, they can immediately deduce that the region responsible for that change must be incredibly compact, smaller than the distance light can travel in that same number of days. By studying these rapid fluctuations, primarily in X-rays which originate from the innermost, hottest part of the disk, we can effectively map the structure of the engine room itself, placing stringent limits on the size of the accretion flow just outside the event horizon of the black hole. This adds a thrilling, real-time dimension to the central paradox of our video. We are not just looking at a static picture of a dark object creating light. We are watching that process unfold dynamically. The flickering and flaring are the live feedback of a frantic, chaotic, and unimaginably powerful system, constantly wrestling with the laws of physics. Each change in brightness is a coded message, a clue about the conditions in the most extreme gravitational environment in the universe, allowing us to piece together the intricate dance of matter and energy that transforms the ultimate darkness into the most brilliant light. For billions of years, a galaxy grows by carefully converting its vast reservoirs of cold gas into brilliant new stars, a steady process of cosmic creation. But then, the monster at its center awakens. As a supermassive black hole enters its quasar phase, it doesn't just light up the galactic core, it seizes control of the entire galaxy's destiny, unleashing forces that can either catalyze a new wave of stellar birth or bring it to a screeching, permanent halt. This profound influence, known as feedback, transforms the black hole from a passive consumer into an active galactic governor, and it solves a major puzzle in astronomy: why massive galaxies aren't even larger than they are. The primary tool of this governance is the quasar's immense outflow. We've already marveled at the relativistic jets shooting from the poles, but the black hole also drives powerful, wide-angle winds of superheated gas that blast outward from the accretion disk itself. These aren't gentle breezes, they are hurricane-force torrents of energy that can sweep through the galaxy at thousands of kilometers per second. This hot wind slams into the galaxy's remaining reservoirs of cold, dense gas, the very raw material needed to form new stars. The effect is twofold. First, the wind violently compresses some of these gas clouds. Imagine a powerful gust of wind hitting a pile of leaves, scattering some but also pressing others tightly together. This sudden compression can actually trigger gravitational collapse, starting the formation of new stars in a brilliant burst of activity. In this scenario, the quasar acts as a cosmic midwife, its violent outburst directly responsible for a wave of stellar birth. But more often, the quasar's influence is not creative but profoundly suppressive. The immense energy carried by these outflows doesn't just push gas around, it heats it to extremely high temperatures. For a gas cloud to collapse under its own gravity and form a star, it needs to be cold and dense enough for gravity to win. When a quasar's wind heats this gas, it prevents that collapse. The individual gas particles are given so much thermal energy that they effectively resist gravity's pull, remaining a hot, diffuse cloud forever unable to coalesce into a star. In even more extreme cases, the quasar's output is so powerful that it doesn't just heat the gas, it completely expels it. These galactic-scale outflows can drive a substantial fraction of the galaxy's entire gas supply out into the intergalactic medium, robbing the galaxy of its future fuel. This process, known as quenching, effectively shuts down star formation for good. The galaxy, starved of the cold gas it needs, enters a long, quiet retirement, its population of stars slowly aging toward a redder and dimmer future. This feedback loop creates a remarkable and self-regulating balance, a cosmic symbiosis between the black hole and its host. A galaxy with too much cold gas falls into the central black hole, feeding it and igniting the quasar. The brilliant quasar then activates, heating or expelling that very gas, which eventually starves the black hole and causes the quasar to shut off. Without new fuel, the black hole goes dormant, allowing gas to gradually cool and accumulate once more, potentially starting the cycle again. This elegant dance explains why we don't see endlessly massive galaxies. The central black hole acts as a built-in thermostat, preventing the galaxy from growing too large by periodically turning on and blowing away its own fuel supply. This intimate connection is why astronomers now find a tight correlation between the mass of a galaxy's central black hole and the mass of the stars in its central bulge. The two grew together, their histories inextricably linked by this feedback loop. And this isn't just a dramatic story for faraway galaxies, it's a chapter in our own cosmic history. Our Milky Way galaxy hosts a supermassive black hole, Sagittarius, a star. Today, it is relatively quiet, a sleeping giant, but evidence suggests it too had its own active phases in the distant past. Fermi bubbles, enormous, faint structures of hot gas extending thousands of light-years above and below our galactic plane, are likely the fossilized remnants of powerful jets or outflows that erupted from our central black hole millions of years ago. This ancient outburst would have shaped the environment around us, heating gas and regulating how stars formed in the Milky Way's central regions. The brilliant paradox of a light-emitting black hole is therefore not merely a curiosity. It is one of the universe's most fundamental mechanisms of construction and control, a violent and beautiful process that for billions of years has sculpted the galaxies, including our own island home, into the forms we see today. This incredible phenomenon, predicted by Einstein's theory of general relativity, gives us a powerful and almost magical tool, the gravitational lens. Just as a glass lens in a telescope can bend and focus light to magnify a distant object, the gravitational field of a massive foreground galaxy, or even an entire cluster of galaxies, can warp the fabric of spacetime around it, creating a natural cosmic lens. When the alignment is just right, and a distant, brilliant quasar sits almost directly behind this foreground mass from our point of view, the light from that quasar is forced to follow the curved geometry of space on its journey to Earth. This bending effect can distort the quasar's image into spectacular arcs or, even more usefully, split it into multiple magnified copies. For astronomers, this is like being handed a telescope with a vastly more powerful lens, a free upgrade from the universe itself. A typical gravitational lens can amplify the light of a background quasar by a factor of 10, 50, or even more. This allows us to study quasars that would otherwise be too distant and too faint to see in any detail, effectively peering deeper into the early universe than our human-made telescopes would ever allow on their own. But the benefit is far greater than a simple boost in brightness. This magnification lets us resolve fine details in the quasar's structure that are normally completely blurred out by the immense distances involved. We can start to distinguish the brilliant accretion disk from the base of the relativistic jets, mapping the anatomy of the engine with a precision that would otherwise be impossible. Each of the multiple images created by the lens acts as a slightly different sightline through the lensing galaxy, potentially revealing different parts of the quasar's outflow or accretion flow, giving us a more three-dimensional understanding of its dynamics. Beyond just giving us a closer look, these natural telescopes also serve as rigorous laboratories for testing the very laws of physics that predict them. By carefully measuring the positions, brightness, and time delays between the multiple images of a lensed quasar, astronomers can perform exquisite tests of general relativity. The precise way the light is bent tells us about the distribution of mass in the foreground lensing galaxy, including its dark matter halo. This has become one of the key methods for mapping the invisible dark matter that makes up the majority of a galaxy's mass, providing crucial evidence for its existence and distribution. Furthermore, because the different light paths of the multiple images are slightly different lengths, the light from each copy arrives at Earth at a slightly different time. If the quasar flickers in brightness, which they often do, we will see that flicker play out in one image and then later in another. By meticulously measuring this time delay, we can calculate the expansion rate of the universe itself, providing an independent measure of the Hubble constant, one of the most important numbers in cosmology. In the context of our central paradox, gravitational lensing provides a unique and powerful observational avenue. It takes the brilliant, mysterious light of a quasar, and by stretching and magnifying it through the gravity of an intervening galaxy, gives us the tools to dissect that light with far greater clarity. It allows us to probe the immediate environment of the supermassive black hole, test the fundamental theory of gravity that describes its existence, and even measure the large-scale structure of the cosmos that houses it. This cosmic magnifying glass doesn't just show us more, it reveals deeper layers of connection, showing how the gravity of one object can illuminate the secrets of another, and in doing so, helps us unravel the beautiful contradiction of a darkness that creates the most profound light. To fully appreciate the staggering energy output of a quasar, it helps to place it alongside other titans of cosmic violence. The universe is a stage for spectacularly energetic events, each with its own unique brand of power and destruction. Consider the supernova, the final, explosive death throes of a massive star. In a matter of seconds, a supernova can release as much energy as our Sun will over its entire 10 billion-year lifespan, briefly outshining its entire host galaxy. It is a catastrophic, universe-shaking event that forges heavy elements and scatters them across space, seeding future generations of stars and planets. Yet for all its raw, instantaneous power, a supernova is a flash in the pan. Its brilliant light fades over weeks or months, a spectacular but fleeting firework in the cosmic dark. Then there are gamma-ray bursts, arguably the most powerful singular explosions since the Big Bang itself. These events, thought to be caused by the collapse of a massive star into a black hole or the merger of ultra-dense neutron stars, concentrate an almost unimaginable amount of energy into two narrow beams of high-energy radiation. For a few seconds, a gamma-ray burst can shine with a luminosity millions of times greater than even a supernova, making it the brightest electromagnetic event known to occur in the universe. The energy release is so focused and so intense that if one were to occur within a few thousand light-years of Earth, it could potentially strip away our planet's ozone layer with devastating consequences for life. But like a supernova, a gamma-ray burst is an ephemeral phenomenon. Its incredible brilliance is measured in seconds or minutes before it vanishes, leaving behind only an afterglow that slowly fades away. This is where the quasar stands apart, not in a single, momentary peak of power, but in its breathtaking endurance. A quasar is not a brief explosion, it is a sustained eruption. It is a cosmic hurricane that rages for millions of years. While a supernova might outshine its galaxy for a few weeks, a quasar does so continuously for epochs that dwarf the entire history of human civilization. Its energy output is not a sudden detonation but a constant, roaring river of radiation flowing from the accretion disk and jets. To match the total energy released by a typical quasar over its multi-million-year lifetime, you would need to detonate a supernova every single second for thousands of years. This incredible longevity transforms the quasar from a mere event into a fundamental era in a galaxy's life, a defining chapter of violent growth and transformation that shapes its future forever. This comparison elevates the central paradox from a fascinating curiosity to a profound mystery. A supernova's light comes from the frenzied nuclear fusion in a dying star's core. A gamma-ray burst's energy is unleashed in the hyper-violent birth of a black hole or the collision of stellar corpses. Their power sources, while extreme, are at least conceptually understandable within the framework of stellar physics. But a quasar's light has a far more counterintuitive origin. It is not powered by fusion or a one-time collapse. It is powered by gravity itself, the same force that creates the ultimate darkness. The energy we see is the gravitational potential energy of matter falling into the abyss, converted into light with staggering efficiency in the chaotic maelstrom just outside the point of no return. The most transiently bright events in the universe are born from fire, but the most persistently bright object is born from a darkness so complete it traps light forever. This is the scale of the contradiction that captivates astronomers and the public alike. It challenges our very definitions of creation and destruction, showing us that in the cosmos, the most profound darkness can be the engine for the most enduring light. The journey to unravel the deepest secrets of quasars is far from over. In many ways, it is just beginning, and the next chapter will be written by a new generation of telescopes so advanced they border on the miraculous. These are not merely incremental improvements, but revolutionary instruments designed to see the universe in ways we've only dreamed of, pushing the boundaries of both technology and human comprehension. At the forefront of this new era is the James Webb Space Telescope, a marvel of engineering that has already begun to transform our view of the cosmic dawn. Unlike its predecessor, Hubble, which primarily sees in visible and ultraviolet light, Webb is an infrared telescope, and this gives it a unique superpower for studying the most distant quasars. The expansion of the universe stretches the light from these incredibly remote objects, shifting their emissions from ultraviolet and visible light into the infrared part of the spectrum. Webb is perfectly designed to catch this stretched light, acting as an ultimate time machine to witness the very first supermassive black holes as they were turning on, feasting in the infant cosmos. With its colossal gold-coated mirror and exquisitely sensitive instruments, Webb can dissect the light from these primordial quasars with breathtaking precision. It can analyze the chemical composition of the gas in their accretion disks and outflows, searching for the earliest heavy elements forged in the first generations of stars. Perhaps most importantly, it can peer through the veils of dust that often obscure the inner regions of active galaxies, giving us a clear view of the feeding process itself. By studying quasars at the moment they are first regulating the growth of their host galaxies through feedback, Webb may finally reveal the exact trigger that awakens a sleeping giant and how that violent outburst so profoundly shapes galactic evolution, answering the question of how this paradox of darkness and light became a fundamental force in building the universe we see today. While Webb explores the infrared sky, another colossal project is taking shape on the ground, one that will listen to the universe rather than look at it. The Square Kilometre Array, or SKA, is not a single telescope but a vast network of thousands of radio antennas spread across 2 continents, in South Africa and Australia. When completed, it will form the most sensitive radio telescope ever built, with a total collecting area of, as the name suggests, a square kilometre. This immense sensitivity will allow the SKA to map the sky in radio waves with unprecedented speed and detail, and for quasar research, its potential is staggering. Radio waves are the signature emission of the relativistic jets that scream away from the poles of active black holes. The SKA will be able to image these jets with a clarity we have never achieved, tracing the flow of energy from its launch point mere light hours from the event horizon all the way out to the gigantic lobes where it dissipates into intergalactic space. This incredible resolution will let us finally test our theoretical models of jet formation against cold, hard observation. We will be able to watch how the jets evolve over time, see how they interact with the interstellar medium, and potentially even witness the elusive magnetic reconnection events that are thought to power their brightest flares. Furthermore, by combining the SKA's radio observations with data from telescopes like Webb and Chandra that see in other wavelengths, we can build a complete multi-wavelength portrait of a quasar's activity, understanding how the processes in the accretion disk directly influence the power of the jets. This holistic view is crucial for solving the puzzle of how black holes spin and the geometry of magnetic fields conspire to create these cosmic particle accelerators, moving us from broad theory to precise, observed mechanics. The synergy between these great observatories and others, like the upcoming Nancy Grace Roman Space Telescope and the Vera C. Rubin Observatory, promises to transform quasar research from the study of individual marvels to a population-level science. These telescopes will conduct vast, automated surveys of the entire sky, discovering millions of new quasars and tracking their variability over years. This enormous dataset will allow us to see the full spectrum of black hole activity, from the faintest smoldering to the most violent outbursts, and understand how a quasar's life cycle unfolds over cosmic time. We will be able to statistically link the properties of the black hole, its mass and spin, to the power of its jets and the impact of its feedback on the host galaxy, uncovering the fundamental rules that govern these engines. The ultimate goal, of course, remains to peer directly into the heart of darkness itself, to image the event horizon of the supermassive black hole at the center of a quasar. The Event Horizon Telescope's first image of the black hole in Galaxy M87 was a historic triumph, but that object is a relative gentle giant. The EHT collaboration and future very long baseline interferometry projects are now setting their sights on much more active and powerful targets, like the quasar at the core of the galaxy Centaurus A, famous for its gigantic, spectacular jets. To see the shadow of the black hole against the brilliant glow of its own accretion disk in such a dynamic system would be a monumental achievement, directly linking the incomprehensible gravity of the singularity to the incredible light show it produces. It would provide the most direct possible test of general relativity in these extreme environments, and might even offer clues about the nature of the mysterious singularity at the center. Each new observation, each new dataset, brings us closer to a complete understanding of this beautiful paradox, proving that the universe's greatest mysteries are not impenetrable walls but invitations to explore further, to look deeper, and to continually redefine the limits of what we know. Perhaps one of the most beautiful aspects of this cosmic paradox is its unique power to transcend the world of academic research and ignite a spark of wonder in the hearts and minds of people everywhere. The very idea of a darkness so profound that it gives birth to the universe's most brilliant light is a concept that resonates on a deeply human level, blending scientific awe with a sense of philosophical poetry. This inherent fascination makes quasars and black holes a gateway, a perfect entry point for educators and science communicators to invite the public into the thrilling story of our universe and our quest to understand it. Across the globe, planetariums harness this power every day. Under their vast domes, audiences are transported from their seats to the very edge of a supermassive black hole. With state-of-the-art digital projections, we can witness the formation of a brilliant accretion disk, see the relativistic jets erupt in slow motion, and journey through a lensed galaxy to see multiple images of a single, distant quasar. These are not just lectures, they are immersive experiences that make the abstract tangible. The collective gasp from a crowd as they see a star ripped apart by tidal forces is a testament to the raw emotional power of these cosmic stories. Planetarium shows transform complex astrophysics into a shared, visceral spectacle, making everyone feel like an explorer on the greatest adventure of all. This sense of exploration continues in the documentaries that bring these wonders into our living rooms. Narrated by charismatic hosts and rendered with breathtaking visual effects, films and series take us on journeys to the most extreme environments imaginable. We get to meet the scientists behind the discoveries, to see the passion in their eyes and share in their moments of frustration and triumph. These stories do more than just present facts. They humanize the scientific process, showing it as a grand, ongoing detective story full of wrong turns, sudden breakthroughs, and collaborative spirit. They make it clear that science is not a static set of answers in a textbook, but a dynamic, ever-evolving conversation about the nature of reality itself. And now that conversation is one that anyone can join, thanks to the rise of citizen science projects. Platforms like Zooniverse have democratized discovery, allowing anyone with an internet connection to contribute to real astrophysical research. A volunteer might be the first person to ever lay eyes on a newly lensed quasar, spotting the telltale multiple images in a telescope survey while scrolling through images on their laptop. Another might help classify the subtle variations in the light curves of distant active galactic nuclei, data that could help astronomers measure the mass of a black hole or understand the stability of its accretion disk. This is no longer passive learning, it is active participation. It transforms the public from an audience into a collaborator, fostering a profound personal connection to the cosmos and a deeper appreciation for the meticulous work that underpins every headline-making discovery. This broad engagement is more crucial now than ever. In an age of complex global challenges, fostering a basic scientific literacy and a shared sense of wonder for the universe is a vital societal goal. The story of the quasar does this beautifully. It teaches us about the fundamental laws of physics, the importance of evidence-based inquiry, and the value of international collaboration. But it also speaks to something more, our innate need to look up at the vastness of space and feel not fear, but an insatiable curiosity. It reminds us that we are part of a grand, mysterious, and breathtakingly beautiful cosmos, and that the drive to understand it is one of the most noble and unifying endeavors of our species. Yet this cosmic contradiction is far more than a mere physical anomaly. It resonates with a profound metaphorical power that has captivated the human imagination for millennia. The image of a black hole, the ultimate symbol of darkness and oblivion, shining with the universe's most brilliant light, challenges our most basic instincts to categorize the world into simple binaries of good and evil, creation and destruction, light and dark. It presents us with a stunning unity of opposites, a concept that philosophers and mystics have pondered for centuries, now given form in the most extreme laboratory of all, the cosmos itself. This isn't just astrophysics. It is a powerful reminder that nature consistently defies our desire for simple categories, revealing a reality that is far more complex, interconnected, and beautifully paradoxical than we often presume. Across cultures and throughout history, humanity has used the duality of light and dark as a fundamental framework for understanding existence. Light represents knowledge, hope, life, and revelation. We speak of a bright idea or seeing the light at the end of the tunnel. Darkness, in contrast, symbolizes ignorance, fear, the unknown, and oblivion. We fear what lurks in the dark corners of the world or talk about dark times. A black hole is the physical embodiment of this ultimate darkness, a voracious nothingness that consumes all. Yet, in a breathtaking twist, this very darkness becomes the catalyst for the most brilliant light we know. It doesn't just coexist with light, it actively creates it, forcing us to reconsider this entire symbolic framework. The universe seems to be telling us that these opposites are not warring factions, but are, in fact, two sides of the same coin. inextricably linked and necessary for the grand cosmic dance to unfold. The darkness is not an end, but a transformation, a crucible where matter and energy are remade into new forms. This idea finds powerful echoes in ancient wisdom traditions. In Taoist philosophy, the familiar yin-yang symbol beautifully illustrates this principle of dynamic balance. The black yin contains a seed of white yang, and the white yang contains a seed of black yin. They are not static enemies but fluid, interdependent forces, each containing the essence of the other and giving rise to one another in an endless cycle. A black hole emitting light is a cosmic yin-yang, a literal manifestation of this ancient insight. Similarly, in alchemical traditions, the pursuit of the philosopher's stone was a metaphorical journey of transformation, taking base, dark matter, and through a great struggle, transmuting it into gold, a symbol of enlightenment and perfection. The accretion disk around a black hole is nature's ultimate alchemical furnace, performing this very feat on a cosmic scale, turning the base matter of stars into the pure energy of light. The paradox also invites deep reflection on the nature of existence and perception. What does it mean for something to be truly a dark or light? A black hole is dark because it traps light, but it is precisely this trapping, this intense gravitational pull, that creates the conditions for the incredible light show we observe. Its darkness is the cause of its light. This challenges our perception of reality, suggesting that what we see is often just the surface effect of a much deeper, hidden process. The brilliant quasar is the visible expression of the invisible black hole's power. It reminds us that the most important forces in the universe, like gravity, dark matter, and even the laws of physics themselves, are often invisible to us, yet they shape everything we can see. Science, in this light, becomes a tool not just for calculation, but for revelation, pulling back the curtain on the hidden mechanics of reality and showing us a world far more wondrous and interconnected than our everyday experience suggests. Ultimately, the story of the light-emitting black hole is a profound narrative about creation born from destruction. It is a theme that runs through the entire cosmos, from the supernova explosions that scatter the elements of life across space to the galactic collisions that trigger new waves of star birth. The universe repeatedly shows us that endings are also beginnings, that loss can fuel gain, and that from the deepest voids can spring the most radiant light. This isn't just a comforting thought, it's a fundamental law of cosmic evolution. The black hole, once the ultimate monster in our scientific mythology, is revealed to be a vital cosmic architect. Its destructive appetite is the very engine that powers beacons to illuminate the early universe, regulates the growth of galaxies, and seeds the cosmos with the energy needed for structure and complexity to emerge. In its terrifying darkness, we find a strange and beautiful source of light, a perfect cosmic metaphor for the idea that even in the deepest depths, the potential for brilliance and transformation is never, ever lost. For decades, the popular image of a black hole has been that of a cosmic villain, an all-consuming, destructive monster lurking in the void, waiting to devour everything in its path. This idea has been fueled by decades of science fiction, where black holes are often portrayed as terrifying threats, the ultimate endpoint for any unlucky spacecraft that gets too close. And on the surface, this view seems justified. After all, their defining feature is an event horizon from which nothing, not even light, can return. They are the ultimate symbols of finality and oblivion. But this perception, while dramatic, is a profound oversimplification. It ignores the other, far more creative half of their nature, the part that makes them not just consumers, but essential architects of the cosmic landscape. The truth is, a black hole is not a mindless vacuum cleaner, passively sucking in everything around it. Its gravitational influence is incredibly powerful, but also incredibly localized. You could, in theory, orbit a black hole just as safely as you orbit a star, provided you maintain a stable path outside the event horizon. The real action, the part that defines its role in the universe, doesn't happen in the darkness at the center, but in the dazzlingly bright, chaotic, and intensely energetic region just outside it. This is where the black hole's true power is unleashed, not to destroy, but to transform. The immense gravitational pull acts as the universe's most efficient power plant, converting the mass of infalling matter into pure energy through the processes of the accretion disk and the relativistic jets. This isn't merely destruction, it's the most spectacular form of alchemy, turning base matter into brilliant light and raw power. This creative force extends far beyond the immediate glow of the quasar itself. As we've explored, the energy pouring out from an active black hole has a governing effect on its entire host galaxy. The powerful winds and outflows it generates can sweep through vast clouds of interstellar gas, and while this can sometimes shut down star formation, it can also trigger it. By compressing these gas clouds, the black hole's energy can initiate the gravitational collapse that leads to the birth of new stars. It acts as a cosmic regulator, a feedback mechanism that prevents galaxies from growing too large, too fast, and ensures a more measured and sustained evolution. In this role, the supermassive black hole is not a destroyer of worlds, but a guardian of galactic balance. Its violent outbursts directly responsible for sculpting the galaxy's structure and future potential. Perhaps the most profound creative contribution of black holes lies in their role as cosmic beacons. The incredible luminosity of quasars, powered by supermassive black holes, allows them to be seen from the farthest reaches of the observable universe. Their light travels for billions of years, acting as a backlight that illuminates the faint, wispy tendrils of the cosmic web, the vast network of gas filaments that connects all galaxies. Without these brilliant, distant quasars, we would have no way to map this invisible structure or study the composition and evolution of the universe on its largest scales. The darkness of the black hole, therefore, creates the light that allows us to see everything else. This shift in perspective, from mindless monster to essential cosmic architect, is crucial to understanding the true nature of our universe. It moves us beyond simple stories of good and evil, creation and destruction, and into a more nuanced and beautiful reality where these forces are deeply intertwined. A black hole embodies the ultimate paradox. It is a place where the laws of physics push matter and energy to their absolute limits, resulting in both an absolute end and a magnificent, life-giving beginning. It teaches us that in the cosmos, destruction and creation are not opposites, but partners in an endless dance, and that from the greatest darkness can come the most illuminating light. At the heart of this dazzling paradox, where darkness births light, lies a set of powerful mathematical relationships that transform the abstract into the astonishingly real. While we often picture the cosmic drama through stunning visualizations, it is the underlying equations that provide the true blueprint for this incredible energy conversion, and they reveal an efficiency that dwarfs anything else in the universe. The key to unlocking this power is perhaps the most famous equation in all of science, E equals mc squared. This deceptively simple formula, given to us by Albert Einstein, is the fundamental rulebook for the entire process. It tells us that mass and energy are two forms of the same thing, and that a tiny amount of mass can be converted into a colossal amount of energy. The c in the equation represents the speed of light, an enormous number, about 299 million meters per second, and because it is squared, the conversion factor becomes almost unimaginably large. This means that even a small handful of matter contains within it the energy equivalent of many powerful nuclear bombs. But how does a black hole actually tap into this potential? This is where the concept of accretion luminosity comes into play. The luminosity, or total light output, of an accretion disk isn't just random. It can be calculated with a specific formula that depends on three things: the rate at which matter is falling onto the black hole, the mass of the black hole itself, and the efficiency of the process. The efficiency is the real star of the show here. It represents what fraction of the infalling matter's rest mass is successfully converted into radiation. For comparison, the process of nuclear fusion that powers our sun is incredibly powerful, but it is also incredibly inefficient by cosmic standards. In the sun's core, only about 0.7% of the mass involved in fusion is transformed into energy. The rest remains as matter. This is why the sun burns through its fuel so slowly over billions of years. The accretion disk around a black hole operates on a completely different level of efficiency. Because the matter is spiraling inward through an intense gravitational field, it loses a tremendous amount of gravitational potential energy. This energy doesn't just vanish, it has to go somewhere, and it is converted into the heat and light that make the disk shine. The theoretical maximum efficiency for this process is a stunning 40% for a standard accretion disk around a maximally spinning black hole. This means that for every kilogram of material that crosses the event horizon, 0.4 kilograms worth of pure energy is released as light and other radiation before it vanishes. To put that in perspective, if you could somehow feed a black hole a single donut, the energy released from its accretion disk would be greater than the yield of a multi-megaton nuclear weapon. This staggering efficiency is why a relatively modest amount of infalling matter, perhaps just a few solar masses per year, can generate enough light to outshine an entire galaxy containing hundreds of billions of stars. The mathematics reveals that it is not the sheer volume of food that matters most, but the incredible efficiency of the digestive system. The black hole's gravity provides the ultimate setting for extracting every last joule of energy from its meal. Turning mere mass into the most brilliant and persistent light shows the universe has to offer. While the quest for life beyond Earth often focuses on the gentle, steady light of sun-like stars, we must also consider the impact of the universe's most violent events. The staggering energy output of a quasar introduces a fascinating and terrifying variable into the cosmic equation of habitability. Imagine a world orbiting a star in a galaxy whose core suddenly ignites into a quasar phase. The planet, once bathed in the gentle radiation of its local sun, would now be exposed to a second, far more malevolent source of light. From across the galaxy, the quasar would flood the entire system with a torrent of high-energy radiation, intense ultraviolet light, X-rays and gamma rays, capable of shredding DNA and stripping away planetary atmospheres with ease. This isn't just a minor environmental stressor, it is an existential threat that could effectively sterilize entire swaths of a galaxy, wiping the slate clean of any nascent life and preventing new life from gaining a foothold for millions of years. This scenario paints quasars as the ultimate agents of cosmic sterilization, but their influence might be more nuanced, a paradoxical blend of destruction and creation. The same powerful outflows and jets that can scour a galaxy clean of its gas might also play a role in seeding the cosmos with the very ingredients necessary for life. The frenzied environment of the accretion disk and the relativistic jets are factories for heavy elements, forging atoms through intense processes and then scattering them far and wide into the intergalactic medium. When these enriched materials eventually cool and become incorporated into new generations of stars and planets, they bring with them the essential elements like carbon, oxygen, and iron that are the building blocks of life as we know it. In this indirect way, the death of one world, or even one galactic neighborhood, at the hands of a quasar's fury could ultimately provide the raw materials for life to arise elsewhere, on a younger world around a newer star in a far distant future. Fortunately for us, and for the prospects of life in the universe at large, the era of peak quasar activity is largely behind us. The universe was a much more dangerous place 10 billion years ago, when quasars were far more common and galaxies were crowded closer together. Today, most supermassive black holes, including the one at the heart of our Milky Way, are relatively quiescent. The average distance between galaxies is now so vast that even if a distant quasar were to flare up, its radiation would be spread so thin across the immense expanse of space that by the time it reached another galaxy, it would be a negligible background whisper, utterly dwarfed by the light of the local star. The sheer rarity of these events in the modern universe significantly increases the chances that life has had long, uninterrupted periods to evolve and thrive on countless worlds without facing such a catastrophic interruption. This connection between quasars and astrobiology beautifully ties our central paradox back to the human question of our place in the cosmos. It expands the narrative beyond the pure physics of gravity and light and into the realm of biological potential. It makes us consider the fragility of life in a universe that contains such unimaginable power, and it underscores the incredible series of fortunate circumstances that have allowed our own planet to enjoy a relatively stable, peaceful existence for the billions of years necessary for intelligent life to emerge. The darkness that creates light also has the power to extinguish it, reminding us that we are not just inhabitants of a galaxy, but subjects to the grand and sometimes violent cycles that govern its evolution. One of the most beautiful evolutions in modern astronomy is the realization that some of the universe's greatest mysteries aren't just being solved by PhDs with access to giant telescopes. They're being unraveled by people just like you from every corner of the globe, in their living rooms, on their lunch breaks, or in their classrooms. This is the world of citizen science, a collaborative movement that has thrown open the doors of discovery and invited everyone to participate in the grand quest for knowledge. For a subject as awe-inspiring and complex as quasars, this public partnership has become an invaluable resource, turning the curiosity of thousands into a powerful engine for scientific progress. Platforms like Zooniverse have been at the forefront of this revolution, creating a digital bridge between the vast, overwhelming streams of data collected by observatories and the unique pattern recognition skills of the human brain. A professional astronomer might have a catalog of 1 million images from a sky survey, each one potentially containing a distant quasar, a gravitationally lensed system, or a strange, variable object. No research team, no matter how large, could possibly examine each one with the careful, discerning eye of a person. This is where the global community steps in. A volunteer might log on to a project like Galaxy Zoo and be presented with a beautiful, swirling image of a distant galaxy. Their task is simple yet profound: classify its shape. Is it a spiral, an elliptical? Does it show signs of a merger? Or does it have something even more unusual at its core? This is where the magic happens. In one famous case, a Dutch schoolteacher named Hanny van Arkel was classifying galaxies when she noticed a strange, glowing green cloud near a distant spiral galaxy. It didn't look like anything she'd seen in the tutorial, so she flagged it in the project's discussion forum. This single act of curiosity, this willingness to say, "This looks odd," led to the discovery of an entirely new class of astronomical object, now called Hanny's voorwerp, which is Dutch for Hanny's object. It turned out to be a massive cloud of gas, illuminated by the intense light of a quasar that had since faded, a sort of cosmic echo from a brilliant outburst that occurred tens of thousands of years ago. This wasn't a discovery made by a multi-million-dollar machine. It was made by an attentive person who was given the tools to look and the platform to ask. The work doesn't stop with classifying galaxy shapes. Specific projects are designed to hunt for the most extreme objects in the universe. Volunteers are trained to look for the subtle, telltale signs of gravitational lensing, those rare and precious alignments where a foreground galaxy's gravity bends the light of a distant quasar into multiple arcs or distinct mirrored images. By sifting through countless images, citizen scientists can identify these cosmic miracles, which are then flagged for professional astronomers to follow up on with the world's most powerful telescopes. Other projects focus on spectroscopy, asking volunteers to examine the intricate barcode-like lines in a quasar's spectrum to help measure redshifts or identify the chemical fingerprints of elements in the gas clouds that lie between us and the quasar. Each classification, each click, is a tiny but vital contribution to a massive statistical dataset, helping to map the large-scale structure of the universe and trace the distribution of matter across cosmic time. This model of distributed research does more than just accelerate the pace of discovery. It fundamentally changes the relationship between science and society. It demystifies the scientific process, showing that it is not a monolithic, impenetrable institution, but a methodical, sometimes tedious, but ultimately thrilling process of collective problem solving. It allows a retiree in Tokyo, a student in Brazil, and a bus driver in Norway to all become active participants in the same project, working alongside lead researchers at premier universities. They aren't just playing a game, they are processing real data that leads to real papers published in prestigious scientific journals, often finding their names listed among the co-authors. This shared ownership of discovery fosters a profound and personal connection to the cosmos, transforming abstract wonder into tangible contribution. It proves that the drive to understand the universe is a universal human trait, and that the paradox of a black hole that shines is a puzzle we are all invited to help solve together. Long before we had the mathematics to describe an event horizon or the telescopes to observe an accretion disk, humanity was already telling stories about cosmic voids and brilliant lights, instinctively reaching for metaphors to explain the profound mysteries of existence. This deep-seated need to make sense of the unknown is why quasars and black holes have so powerfully captured our collective imagination, leaping from the pages of scientific journals into the very fabric of our art, our myths, and our most ambitious science fiction. They have become more than just astronomical objects. They are potent symbols, and the roles we assign them in our stories reveal as much about our own hopes and fears as they do about the physics of these gravitational giants. In the realm of science fiction, black holes have often been cast as the ultimate cosmic peril, a narrative trapdoor through which unlucky spacecraft and their crews might vanish without a trace or be hurled into another time or dimension. The iconic film Interstellar offered one of the most scientifically informed and visually stunning depictions yet, presenting the black hole gargantua not just as a threat, but as a beautiful and enigmatic gateway. The filmmakers worked closely with physicist Kip Thorne to ensure the portrayal of the accretion disk and gravitational lensing was as accurate as possible, resulting in a luminous, swirling disk of light that burned itself into the public consciousness. But beyond the science, the black hole served as a profound plot device representing the unknown and the sacrificial journey into the abyss that is sometimes necessary for salvation and discovery. It was both a terrifying void and a conduit for love and connection that transcended the dimensions of spacetime itself, This duality is a common thread. For every story that uses a black hole as a simple hazard, another explores its transformative potential. They are often portrayed as cosmic shortcuts for interstellar travel, or as mysterious engines of change that alter reality itself. Quasars, with their even more dazzling energy output, frequently appear as the power sources for unimaginably advanced civilizations, or as the ultimate destination for a galactic saga. Their incredible luminosity makes them the perfect natural wonder to instill a sense of cosmic awe, a visual shorthand for the sheer scale and power of the universe that dwarfs human endeavors. These narratives allow us to safely confront the terrifying vastness of space from the comfort of our homes, transforming existential dread into thrilling adventure. Beyond the screen and the page, these objects have deeply influenced visual art and music, providing a new vocabulary for the sublime. Artists like NASA's own data illustrators translate the cold numbers of astrophysics into breathtaking visualizations that walk the line between scientific representation and abstract art. The ethereal, hypnotic patterns of an accretion disk or the violent, linear thrust of relativistic jets have inspired painters and digital artists to create works that evoke a sense of wonder, mystery, and even spiritual contemplation. In music, composers have tried to capture their essence through sound, from the ominous, droning tones meant to signify the immense gravity of a black hole to the soaring, brilliant crescendos that represent the explosive birth of a quasar. They become muses for expressing feelings that are difficult to put into words, the allure of the unknown, the beauty of chaos, and the awe of confronting something infinitely greater than ourselves. Perhaps most interestingly, we can look back and see how ancient myths and religious stories presaged these modern concepts. Cultures across the world have stories of bottomless pits, underworld portals, and devouring monsters archetypes that resonate strongly with our modern understanding of black holes. The Norse wolf Fenrir, who consumes the sun, or the Hindu goddess Kali, both creator and destroyer, embody that same paradoxical union of life-giving and all-consuming power that we see in the astrophysical feedback of a quasar. It is as if the human psyche has always been prepared for the discovery of such objects, using the language of story and symbol to grapple with the concept of an inevitable, inescapable end that is also a part of a larger cosmic cycle. This rich cultural tapestry does more than just entertain us. It completes the story of scientific discovery. The equations tell us how a black hole behaves, but the art and the myths tell us how it feels to live in a universe that contains such things. They represent a different but equally important way of knowing. By creating these stories and symbols, we are not running from the science. We are integrating it into our human experience, making it part of our culture and giving it meaning. The black hole, in its absolute darkness, becomes a screen onto which we project our deepest questions about death, destiny, and transformation. The quasar, in its blinding light, becomes a symbol of ultimate power, creation, and the audacious hope that even in the most distant voids, light can still be found. Together, they show that our response to the universe's greatest mysteries is not just to calculate and observe, but also to dream, to create, and to wonder. Yet as we reach for the stars with our most powerful instruments, we must also pause to consider our footprint, for the very tools we use to unravel the cosmos can also, ironically, obscure our view. The quest to understand the universe's most brilliant paradoxes comes with a profound responsibility, a need for ethical stewardship that ensures our own activities do not inadvertently blind us to the faint, distant whispers of light from objects like quasars. This isn't just about building bigger telescopes, it's about protecting the pristine conditions that allow us to see at all. balancing our insatiable curiosity with a mindful respect for the silent canvas of space. One of the most immediate and growing challenges is the proliferation of artificial light here on Earth. The glow from our cities, our streets, and our infrastructure creates a pervasive veil of light pollution that washes out the delicate light of distant stars and galaxies. For professional observatories, this means a significant loss of data. The faint, nuanced light from the most distant quasars, which has traveled for billions of years to reach us, can be utterly drowned out by the scattered glare of a nearby parking lot. This isn't a minor inconvenience. It actively degrades the quality of our observations, making it harder to measure subtle variations in a quasar's brightness or to analyze the faint spectral lines that reveal the composition of the early universe. The fight against light pollution has led to the creation of dark sky preserves in remote locations, but it is a constant battle requiring careful urban planning and the widespread adoption of shielded, downward-facing lighting to protect our window on the cosmos. It is a poignant reminder that to see the grandest lights in the universe, we must first be willing to temper our own. The challenge extends far beyond our atmosphere into the realm of radio silence. Quasars are not just brilliant in visible light, they are also powerful emitters of radio waves, and this part of their signature is vital for studying their relativistic jets. Yet here on Earth, our civilization is a cacophony of radio noise, from cell phone towers and satellite television to radar installations and Wi-Fi networks. This creates radio frequency interference, or RFI, which can easily swamp the faint cosmic signals astronomers are trying to detect. Protecting specific radio frequency bands, known as radio quiet zones, is absolutely essential. This requires international cooperation and stringent regulations to ensure that our thirst for communication does not deafen us to the universe. It's a delicate negotiation, allocating slices of the radio spectrum for human use while preserving clean, silent channels reserved exclusively for listening to the cosmos. And now, a new threat is literally taking flight: the rapid deployment of mega constellations of satellites. Thousands of these artificial objects are being launched into low Earth orbit to provide global internet coverage. While a noble goal for connectivity on Earth, these constellations have a devastating side effect for astronomy. Their highly reflective surfaces catch the sunlight long after the ground has fallen into darkness, creating long, bright streaks across telescope images. For wide-field survey telescopes like the Vera C. Rubin Observatory, which is designed to scan the entire sky every few nights, these streaks can ruin a significant fraction of their exposures, potentially masking the very transient events or faint, distant quasars they are built to discover. The astronomical community is now urgently engaged with satellite operators, advocating for mitigations like darker coatings, different orbital orientations, and even automated software to mask the trails. But it represents a fundamental shift in the environment of near-Earth space, turning a once pristine observing platform into a crowded and reflective obstacle course. These ethical considerations force us to confront a larger philosophical question about our place in the universe. Are we merely passive observers, or are we now active shapers of our own cosmic perspective? Our curiosity drives us to build ever larger telescopes to peer deeper into space and further back in time. But our technological progress on Earth is simultaneously making that task more difficult. This creates a tension between our desire to connect with each other and our desire to connect with the cosmos. It calls for a new kind of ethics, a space environmentalism that considers the impact of our actions not just on our planet, but on our view of everything beyond it. It means making conscious choices, sometimes at a cost, to preserve the clarity of that view for future generations. Protecting our ability to study the faint light of quasars is about more than just astronomy. It is about safeguarding a fundamental human experience, the ability to look up at a dark, starry sky and feel a sense of wonder, to ask profound questions about our origins, and to continue the timeless pursuit of knowledge, ensuring that the universe's greatest paradoxes remain within our reach. Solving a puzzle as profound as the light-emitting black hole is not a task for a lone genius working in isolation. It is a monumental endeavor that demands the combined intellect and skills of experts from a breathtaking array of disciplines. Astrophysics, particularly when it comes to understanding quasars, is a truly interdisciplinary symphony. To listen to this cosmic music and understand its score, you need to be a master of many instruments, from the fundamental laws of physics to the cutting-edge tools of computer science and engineering. This collaborative spirit is the very engine of modern discovery, and it's the only way we can hope to unravel a paradox that exists at the very edge of our understanding. Naturally, the foundation is physics. You cannot begin to comprehend the environment around a black hole without a deep grasp of general relativity, the theory that describes how mass and energy warp the fabric of spacetime itself, creating the gravitational pit we call a singularity. This is the stage upon which the entire drama unfolds. But then, to understand the actors on that stage, the superheated plasma of the accretion disk, you need the laws of magnetohydrodynamics, which describe how electrically charged fluids behave under the influence of magnetic fields. And when particles in the jets are accelerated to 99.9% the speed of light, you need special relativity to calculate how their mass increases and time slows down from our perspective. Each layer of physics builds upon the last, creating a complex, interlocking picture of extreme forces. But the actors on this relativistic stage are made of matter, and that is where chemistry makes its essential contribution. When we point our telescopes at a quasar and break its light down into a spectrum, we are essentially taking a forensic sample of its composition. Those dark absorption lines and bright emission lines are the unique fingerprints of specific elements: hydrogen, helium, carbon, iron, and more. Decoding this cosmic barcode is pure analytical chemistry. It tells us what the accretion disk and the surrounding clouds of gas are made of. Finding heavy elements like iron billions of years ago tells a stunning story of rapid chemical enrichment, proof that generations of massive stars had already lived, died in supernova, and seeded the early universe with the building blocks of planets and life long before our solar system even existed. Chemistry provides the inventory of the cosmic workshop, yet we cannot run a real-world experiment on a black hole. We cannot create a supermassive singularity in a lab or generate relativistic jets on demand. This is where computer science becomes our greatest ally, allowing us to build virtual laboratories inside the world's most powerful supercomputers. Researchers write immensely complex algorithms based on the equations of physics and chemistry to create simulations of accretion disks. These are not simple animations. They are numerical models that calculate the movement, temperature, and magnetic properties of billions of individual particles of virtual gas as they spiral inward, allowing us to watch jets form and magnetic fields snap in real time. Without this computational power, our theories would remain elegant but untested mathematical abstractions. Computer science turns them into dynamic, testable models that we can compare against real telescope data. And none of this would be possible without the marvels of modern engineering. The data that feeds the physicists, chemists, and computer scientists comes from telescopes that are themselves breathtaking achievements. Building the mirrors for the James Webb Space Telescope required mastering new techniques in optics and material science to create a surface so smooth and so cold it could detect the faint infrared heat of the earliest quasars. The Event Horizon Telescope is not a single instrument but a global network of radio dishes, from the high deserts of Chile to the volcanoes of Hawaii. Keeping them all synchronized to within a fraction of a second using atomic clocks, and then combining their data using a technique called very long baseline interferometry, is a monumental feat of electrical and software engineering. Engineers designed the lenses, built the detectors, wrote the guidance systems for the rockets that launched them, and created the digital pipelines that bring the precious data back to Earth. This is the beautiful, collaborative reality of modern science. A theoretical physicist might develop a new model for jet formation. An observational astronomer will then use an engineer's telescope to collect the data to test it. A chemist will analyze that data to determine the composition of the jet, and a computer scientist will write a simulation to see if the physicist's model can reproduce the chemist's findings. There are no rigid boundaries. The most exciting discoveries often happen in the fertile spaces between these disciplines, where a chemist asks a physics question or an engineer sees a computer science problem in a new way. This holistic approach is not just helpful for solving the paradox of the light-emitting black hole. It is absolutely essential. It reminds us that the universe does not abide by our human-made categories. To understand its deepest mysteries, we must be willing to bring every tool we have to the table and work together, weaving a single tapestry of knowledge from countless different threads. Behind every monumental discovery about these brilliant enigmas, there are scientists whose curiosity and dedication have driven them to spend a lifetime staring at data, wrestling with equations, and chasing the faintest whispers of light across the cosmos. Their stories are not just footnotes in the history of astronomy, they are the very human heart of the scientific endeavor, filled with moments of frustration, serendipity, and pure, unadulterated wonder. Consider the story of Martin Schmidt himself, the man who first cracked the code of the quasar spectrum. Imagine the pressure he must have felt, staring at that confounding pattern of lines from object 3C273, knowing it was a puzzle that had stumped the entire field. He later described it as a moment of sudden, almost shocking clarity, a leap of intuition that required him to abandon the assumption that these were nearby objects. That single insight, born from years of training and a willingness to think the unthinkable, didn't just solve a mystery, it flung open a door to an entirely new universe, revealing its violent and energetic youth. His journey reminds us that breakthroughs often come not from complex machinery alone, but from a prepared mind daring to see the familiar in a radically new way. Then there is the story of Jocelyn Bell Burnell, who as a graduate student in 1967 discovered the first pulsars, rapidly spinning neutron stars that emit beams of radio waves. While not quasars, her story is a powerful testament to the perseverance and sharp-eyed diligence required in astronomy. She was the one who first noticed the curious, repeating scruff on miles of paper chart data from a radio telescope she had helped build. While others might have dismissed it as interference or noise, she meticulously documented it, pursuing the anomaly with dogged determination until its extraterrestrial origin was confirmed. Her experience, which involved initially being overlooked for the Nobel Prize awarded to her supervisor, also highlights the often unseen contributions and challenges faced by many in the field, especially women of that era. Her grace and dedication in the face of this, and her subsequent monumental career, inspire a generation of scientists to value the discovery itself above all else. We can also look to modern researchers like Dr. Priyamvada Natarajan, a theoretical astrophysicist at Yale University who has dedicated her career to mapping the invisible. Her work on the intricate relationship between dark matter and the growth of supermassive black holes involves creating sophisticated computer models of how these gravitational monsters form and evolve. Her journey is one of intellectual courage, venturing into the most theoretical realms to make testable predictions about the nature of reality. She often speaks about the challenge and the beauty of working on concepts that are, by their very nature, unseeable, using the mathematics of gravity as her guide. Her path from a curious student in India to a leading figure in cosmology demonstrates how a passion for fundamental questions can transcend borders and backgrounds, uniting a global community in the shared quest to understand our universe. These personal narratives share a common thread, a deep and abiding fascination with the unknown, coupled with the resilience to face years of unanswered questions and dead ends. For every celebrated discovery, there are thousands of hours of painstaking, tedious work sifting through data, debugging code, writing proposals for telescope time that may not be granted. The life of an astronomer is far from the romanticized image of someone peering through an eyepiece every night. It is a career of rigorous analysis, collaboration, and patient waiting for the universe to reveal its secrets. Yet, the moments of discovery make it all worthwhile. The thrill of being the first person in history to witness a particular event or to finally see a theoretical prediction confirmed in a data plot is a feeling that fuels a lifetime of inquiry. These stories of passion and perseverance ground the grand cosmic paradox in a deeply relatable human experience. They remind us that science is not a cold, impersonal collection of facts, but a living, breathing journey undertaken by people who are driven by the same awe and curiosity that we all feel when we look up at the starry night sky. The best part is, you don't need a billion-dollar telescope to start your own exploration of these cosmic powerhouses. The universe's most brilliant beacons are accessible to anyone with an internet connection and a sense of wonder. Let's talk about how you can become a cosmic cartographer from the comfort of your own home, turning your screen into a portal to the distant universe. One of the most user-friendly and powerful tools is NASA Skyview, which is a free online resource that lets you query a vast database of the entire sky. You can simply type in the name of a famous quasar, like 3C273, the very first one identified by Martin Schmidt, and Skyview will instantly pull up its location and show you what it looks like across different wavelengths of light, from the radio waves that first revealed it to the X-rays that pour from its energetic core. It's like having the combined power of the Hubble and Chandra telescopes at your fingertips, allowing you to see how the same object presents itself to different instruments, revealing facets of its nature that are invisible to the human eye. For a more immersive, real-time experience, nothing beats planetarium software like Stellarium. This is an incredible free application that you can download to your computer or even run on a web browser, and it transforms your device into a dynamic, interactive map of the night sky. You can set your location to anywhere on Earth, fast-forward time to see what the sky will look like tonight or 1,000 years from now, and then use its search function to hunt down quasars. While you won't see them as brilliant points of light like stars, their incredible distance makes them appear faint. Stellarium will accurately plot their positions. You can zoom in and with the database information learn their mind-boggling distances and redshifts. It's a profoundly grounding experience to use the software to find, for example, the quasar that holds the record for the most distant object visible with a large amateur telescope, and then realize that the photons of light hitting your screen from that object began their journey when the Earth was still cooling from its formation. This isn't just stargazing, it's time traveling. The adventure doesn't stop with just looking. You can actually contribute to real scientific discovery through citizen science platforms. Projects on Zooniverse like Radio Galaxy Zoo invite the public to help astronomers identify the supermassive black holes powering distant quasars. You'll be presented with real data from radio telescopes and infrared surveys, and your task is to match the colossal radio jets, which can be vast, extending far beyond their host galaxy, to the infrared light of the galaxy itself. This is a task where the human brain's incredible pattern recognition skills still outperform computers, and by classifying these images, you could be the first person to ever correctly identify the source of a distant quasar's jet, contributing directly to a published scientific paper. It's a thrilling opportunity to move from being a passive observer to an active participant in the process of cosmic discovery, helping to map the invisible structures that these dark engines create. And for those who want to go even deeper, the Sloan Digital Sky Survey offers a public data repository that is nothing short of a treasure trove. Here, you can access the actual spectra of millions of quasars, those intricate barcodes of light that reveal their composition, distance, and velocity. While this requires a bit more learning, there are fantastic online tutorials that can teach you how to read these spectra, how to identify the telltale signature of hydrogen or magnesium, and how to measure the redshift yourself. Imagine the thrill of downloading the data for a quasar, analyzing its light, and independently calculating that it is racing away from us at a significant fraction of the speed of light, all from your own desk. These tools demystify the process of astronomy, breaking down the barrier between professional scientists and the curious public, and empowering you to not just learn about the universe's greatest paradoxes, but to actively engage with them, proving that the quest to understand the cosmos is an adventure open to everyone. So after this incredible journey to the edge of reality itself, what have we truly learned? We set out to solve a beautiful contradiction: how the ultimate cosmic abyss, a place of such profound darkness that it traps light itself, can become the source of the most brilliant illumination in the universe. The answer, as we've seen, doesn't lie within the black hole's event horizon, but in the breathtakingly violent and complex physics that unfolds just outside of it. It's the superheated, churning maelstrom of the accretion disk, where matter is torn apart and gravity's immense power is converted directly into raw radiation. It's the unimaginably powerful magnetic fields, wound into cosmic springs by the black hole's spin, that act as a slingshot to launch jets of matter at nearly the speed of light, beacons that can be seen clear across the cosmos. This is not a simple story of darkness versus light. It is a story of transformation, where the most destructive force in nature becomes, paradoxically, one of its most creative. This revelation does so much more than just solve an astronomical puzzle. It fundamentally expands our understanding of the universe and our place within it. We've learned that black holes are not the simple, destructive endpoints we once imagined them to be. They are dynamic engines, active participants in the life cycle of galaxies. They can govern the birth of new stars, regulate the growth of their galactic homes, and seed the cosmos with the heavy elements that are the very building blocks of planets and life. The existence of quasars shining from the universe's infancy tells us that this process has been shaping cosmic evolution for billions of years, proving that from the very beginning, darkness and light have been engaged in a delicate, intertwined dance of creation and destruction. This ongoing quest, powered by our collective curiosity, is one of the most noble endeavors of our species. It connects us to the first humans who looked up at the starry sky in wonder, and it propels us toward a future of even greater discovery. So the next time you find yourself under a clear night sky, take a moment to simply look up. Remember that hidden within that vast darkness are not just points of light, but profound mysteries and breathtaking paradoxes waiting to be unraveled. The universe is constantly whispering its secrets to those who are willing to listen, to look, and to wonder. Let the story of the light-giving black hole be a reminder that even in the deepest voids, brilliance can be found, and that the greatest secrets are often hidden in plain sight, waiting for a curious mind to bring them into the light. Thank you so much for joining me on this journey to the edge of a black hole and back. If you found this dive into one of the universe's greatest paradoxes as fascinating as I do, then you definitely won't want to miss what's coming next. Make sure to hit that like button and subscribe to the channel, and don't forget to tap the little bell icon so you get notified every time we drop a new video. We're always exploring the biggest mysteries and the latest discoveries in astronomy, from the strange worlds of our own solar system to the farthest, most mind-bending edges of the cosmos. I'd also absolutely love to hear from you down in the comments. What cosmic paradox keeps you up at night? Is it the true nature of dark matter, the possibility of a multiverse, or something else entirely? Let me know what you'd like to explore together next. This is just the beginning of the conversation, and your curiosity is what fuels this